and welcome to the module 4 of computational techniques, and in module 4 we are going to look at nonlinear algebraic equations and computational methods to solve the nonlinear algebraic equations. So let us look at a simple motivating example for this particular problem. This is just a straightforward example of a nonlinear equation 2 minus x plus log of x equal to 0, and essentially what we are intending to do is find the points of intersection of this particular curve with the x axis. So this particular curve intersects the x axis at two different locations. So this one location and this the second location are essentially the solutions to the equation 2 minus x plus ln of x equal to 0. What we intend to do is figure out ways of numerically solving this particular equation. What I have shown over here in the graph is essentially a graphical method. We can employ graphical methods for relatively simple problems, perhaps problems in one or two variables, but when the problems go beyond say a couple of variables, we are not going to be able to use graphical methods, and for in general for more complicated examples we will not be able to use analytical techniques in order to get the solutions. So we resort to essentially using the power of computer and numerical techniques in order to solve this problem. So as I said, the solution is the location where the curve intersects the x axis. Unlike the linear case that we saw in module 3, it is possible to have more than one solution but a finite number of solutions to the equation. For example, in linear algebra, when we looked at the systems, what we found is when the matrix A was non-singular, that means rank of matrix A was equal to n, we could get exactly one unique solution, and when the rank was not equal to n, we could possibly get infinite number of solutions, but we never got multiple finite number of solutions to the problem. However, in disagreement with that observation, what we see in in nonlinear systems is that they can have multiple solutions, and the example is right in front of you. Is now there are two solutions, one at this particular location and the other at this particular location, both of which are the solutions to the equation 2 minus x plus ln x. The first solution is 0.1586 and the second solution is 3.1462. So these are the two solutions to the equation. Okay. The general setup that we are interested in is given a particular function f of x, we are interested in finding out the x that solves the nonlinear equation f of x equal to 0. This is the general setup in a single variable. In general, this f of x could be a closed form expression, as in this particular expression 2 minus x plus ln x. What we mean by closed form expression is that we can express x, we can express f of x explicitly in terms of x. There are a lot of problems in which we may not have a closed form equation, or we may not have an algebraic representation of x, but x can be obtained through certain other numerical means, and we will look at those problems perhaps when we come to module 8 when we discuss about boundary value problems in ordinary differential equations, and when we talk about partial differential equations. But as of now, what happens is, all we need is, given a particular x, we need a method to give us the the function f of x, and as long as we have that, we do not care whether it comes from an expression of the type 2 minus x plus ln x, or whether it comes through any other means. So that is the general setup, and we are interested in finding out the point of intersection of the curve f against the x axis. An example, and the nonlinear systems are extremely common in chemical engineering, for that matter in any engineering systems, and just a simple example that we have taken over here is catalytic reaction taking place in a continuous stir tank reactor, and let us say the catalyst follows a Langmuir-Hinshelwood type of kinetics. Then if we try to get the steady state relationship for the CSTR, where tau, if tau is the residence time, we get inlet concentration divided by tau minus the outlet concentration divided by tau, minus the rate of reaction essentially should be equal to 0 at steady state, and if it follows Langmuir-Hinshelwood kinetics of a particular kind, we have the rate expression expressed in terms of kCa divided by 1 plus capital Kca the whole squared, and this is a nonlinear expression, and because of the presence of this nonlinearity, the overall function f of the concentration Ca becomes nonlinear. So, in general, now when you have to solve an equation of this sort in order to get the concentration of Ca, or in order to get the tau value that will give you a particular Ca, what we will have is essentially a nonlinear equation, a single equation in a single unknown, and we can solve that particular equation through the techniques that we will learn in this module. We will be able to solve those equations and we will get the desired solution for that particular problem. So, that is, for example, in this case that particular solution is going to be the concentration Ca that we are going to get out of this particular reactor if tau is going to be the residence time in this particular cell. Now, that is when we talk about a single variable case. Let us look at the extension to multivariable case. In multivariable case, we do not have just one variable, but we have in general n variables. So, we have x1, x2 up to xn, those are n variables, and for them to have, for the entire system to be a well posed system, we actually need n functions f1, f2 up to fn equal to zeros, which and this particular condition needs to be satisfied. If this condition is satisfied for each of those functions f, at that time we say that the values of x1, x2 up to xn are the solutions to these equations. And we will use a vectorial notation for a multidimensional system, very similar to what we did in module 3. Our x bar is going to be, or in this case I have used a bold-faced x, our x is going to be x1, x2 up to xn. It is going to be a column vector where the n variables form the n rows of that particular vector, and f is also going to be a vector where the first element of f is going to be just f1 computed at x1, x2 up to xn, the second is going to be f2 computed at x1, x2 up to xn, and so on up to fn. And these particular n equations in n unknowns we can write in a shorthand notation in the form f of x equal to 0. Okay, so that is the shorthand notation for this particular system. Okay, so there is a specific reason why we are using this particular shorthand notations, and essentially it is because we are interested for a single variable case in obtaining a numerical technique that will solve the problem and give us the solution x, and in multivariable case we want a technique which is scalable to any general n. It's we are not interested in developing a technique that is suitable only for 2 or 3 or 4 variables, but we in general we are interested in figuring out a technique that can be applied to a large number of variables. Okay, so that's really the overall picture or overall introductory picture behind this solution to nonlinear equations. We will take up another example when we have two equations in two unknowns. This is an example actually of propane combustion in case of oxygen is going to be present in excess. So, if we have propane combustion taking place in an adiabatic continuous reactor, and Ca0 is the concentration of propane at the inlet and Ca is the concentration of propane at the outlet, and tau is the residence time, then this is the overall equation that we get for obtaining the concentration at the exit. This is a nonlinear equation. There are two types of nonlinearity. One nonlinearity comes in because of the Arrhenius type of rate law, because of the exponent of minus E by RT. The other nonlinearity comes in because this is not a first order reaction rate, but it's the reaction kinetics has an order of 1.65. Likewise, so this one is going to be f1 of Ca and T Likewise, we will need an energy balance also. The energy balance will give you the second function F2, and F2 of Ca and T is written over here, and basically this is the heat of reaction term and this is the rate of reaction term. So, this particular product is the total heat that is generated because of the reaction taking place. This is the sensible heat entering into the system at the inlet, and this is the sensible heat exiting from the system at the outlet, and this becomes our overall problem. So, our x bar in this case, if we refer to the previous slide, the f bar in this case becomes f1 and f2, and x bar is just going to be Ca and T, and n in this particular example is nothing but 2. Okay. So, now we are not in general not just restricted to 2 equations, to 2 and 2 unknowns and so on. We can in general have n equations and in n unknowns. Just an example to give you is, for example, we have a distillation column with say 40 trays, then and 2 components. We will have the mass fraction of component A in the liquid, mass fraction of component A in the gas phase, and temperature. These are the 3 variables at each of those stages, and so we will end up with 3 multiplied by 40 is 120 variables. So, we might actually end up with 120 equations and 120 unknowns, and that would be an example of a multidimensional system in nonlinear equations. Okay. Now, all the methods that we are going to look at will follow a certain general strategy of getting this solution, and the general strategy will involve, we will require first an initial guess that is shown by the red dot over here. So, that is going to be an initial guess. We need to either provide an initial guess, or the numerical method that we develop has to also incorporate in it a method to get that particular initial guess. Once we get initial guess, we might either have one initial guess or we might start with 2 initial guesses. So, the first agenda is going to be to start with 1 or 2 initial guesses and then use a particular strategy in order to move that particular initial guess in the direction of the solution. In general, at this point we know how the solution, how the curve looks like, we know what the solution is exactly going to be. So, we can figure out whether or not the particular point is moving towards the solution or moving away from the solution and so on. But in general, we do not, if we do not know what this curve looks like or where the intersection of the curve with the x axis is a priori, we do not know whether the movement is in the direction of the solution or whether it is not. However, what we need is to choose a strategy which will generate the successor moves given a current initial guess and given the function f either in a closed form like this or some method to generate f of x given x. Okay. Now, the next item would be to verify if the stopping criterion is satisfied. In this particular case, the blue dot that we see over here, it is fairly far away from the actual solution if you look at, and if you compute the f of x at that particular point, so this is going to be f of x, that also we realize is fairly far away from 0. We are trying to solve the problem f of x equal to 0, and we will see that f of x in this particular case is fairly far away from 0. So, in this case we will conclude that the stopping criterion is not satisfied, and because the stopping criterion is not satisfied, we will have to go back, solve this particular problem once again using the chosen strategy, again move in the direction of the solution, again verify if the stopping criterion is satisfied, and keep doing this repeatedly, and once the stopping criterion is satisfied, this is going to be the numerical solution that we obtain. Okay. So, that is going to be a general strategy for whichever numerical method that we choose to use in this particular problem. And the general numerical methods that we are going to use for nonlinear equation solving, they fall essentially in 2 different categories. One is known as bracketing methods. Bracketing methods always will employ 2 initial guesses, and the 2 initial guesses are going to bracket the solution. For example, the one initial guess could be over here, the other initial guess could be over here. so that they are bracketing the solution, and we then figure out a way to determine what the next guess is going to be, and the methods that will determine the next guesses. There are two methods that we will cover in this particular module. One is called the bisection method, and the next one would be the regular falsi method. Then there are open methods which either are going to start with one or two initial guesses, and they will try to move towards the true solution, and those methods that we will cover in this particular course is the secant method, the fixed point iteration, and Newton-Raphson method. So what I am going to do initially is cover all these methods for a single variable problem. Then we will talk about cases where these methods are going to encounter certain issues and certain problems in this solution techniques, and we will try to look at some modifications, some extensions of these methods. We will also look at extensions of two of these methods, specifically the fixed point iteration and the Newton-Raphson method. We will look at their extension to multivariable system, and finally something that we are going to do also cover towards the last lecture of this module is root finding. And what we mean by root finding is, given a polynomial expression of this form, for example this is x cube minus 2x square minus x plus 2, we want to find out all the places where this particular curve is going to intersect the x axis. So for example, this particular equation can also be written as x minus 1 multiplied by x minus 2 multiplied by x plus 1, that is the expansion of this particular equation. And so x equal to minus 1, x equal to plus 1, and x equal to plus 2 are going to be all the three values of of x that are going to satisfy this particular equation equal to 0. So the root finding methods are going to rely on some of the techniques that we will cover on the nonlinear equation solving front, and it is going to be essentially an extension of these nonlinear solving methods in order to find all the roots of a polynomial equation. Okay. So that is the overall overview of what we are going to do in the nonlinear equation solving. Okay, so let us look at again the particular curve that we had previously. So we will just look at points that go beyond x equal to 1. There was one more solution below x equal to 1 for that particular curve. We will currently not worry about that, and we will just consider that curve, let us say in this particular form, and this is going to be the solution that we are interested in. We will mark that solution as x star, the star representing that it's the true solution of that particular problem. I'll just write it in larger letters. Okay. Now the bisection method it's a bracketing method Okay. What we mean by bracketing method essentially is that we need two initial guesses such that one initial guess lies to the left of this particular equation, then the other guess lies towards the right of this particular equation. So the first guess that we'll have, let's say, is, and we'll write this as xl, L to represent that it lies to the left of x star, and the other one will write this as xr to represent that xr lies to the right of x star, xr lies to the right of x star. Okay. So these are the two initial guesses that we will start off with. Since it is a bracketing method, these two guesses should lie on either side of x star. So now the question is, how do we know whether these two guesses lie on either side of x star? Well, that is because f of xl is going to have a sign which is different from f of xr. Okay. So in this particular example, f of xl is positive and f of XR is negative in this example. Okay. So, if we multiply, of course, if the curve was reversed, if you can think of a mirror image of this particular curve, in that case our f of xl is going to be negative and f of xr is going to be positive. But if we multiply f of xl with f of xr, because we are multiplying a positive number with a negative number, that particular product we know for sure is going to be negative, irrespective of what type of curve that we get. As long as xl and xr are going to bracket the solution, the product of xl and xr is always going to be negative. Okay. So, rather than looking at this particular criterion to decide whether xl and xr lie on either side of x star, the criterion that we will use to determine that is going to be f of xl multiplied by f of xr should be less than 0. Okay. So, the first thing that we need to do is to determine the initial guesses, and the initial guesses are such that f of xl multiplied by f of xr should be less than 0. From this point onwards I am going to use a shorthand notation f superscript l in the bracket to represent f of xl. So, for f of xl I will just use a shorthand notation f of l. This is going to be our initial guess. The second step that we said is to find out how we will move these from these, starting at these two initial guesses, how we will get the next solution, so that we move the initial guess to the next guess. Okay. And the bisection method is also known as midpoint method, and the idea behind my bisection method is quite simple, is you move from xl and xr to the midpoint between xl and xr. So, in this particular case the midpoint, let us say, lies over here, and that is going to be our x2. Okay. So, our x2 is going to be our xl plus xr divided by 2. So, that is going to be the midpoint of the particular expression of the particular line connecting xl and xr. Okay. So, that is going to be our x2. The next question is to check whether if the solution is converged. Okay. In this particular example that I have drawn pictorially, what we see is that the solution is not converged because we have not really reached the true solution, or the other way to look at this is that we are still far away from our f2, our f of x2 is still far away from 0. Okay. So, there are two ways to determine whether the solution is reached or not. One method to determine is whether f of 2 minus f of l, whether that is less than some predetermined value epsilon. Okay. Or the other method is whether I'm sorry, this should be x of 2 minus x of l, the previous solution and the current the new solution, whether they are less than a predetermined value epsilon. Or the other way, other criterion that we can use is whether the function f of x2, whether or not that is less than certain other value delta. Okay. We can use either or both of these methods. Some of the more advanced numerical techniques that are available in various packages such as MATLAB and so on, they will use both these criteria and check both these criteria and determine whether the solution is reached or not. In general, as we had done in module 2, what we had said is we are interested in finding out how close is our new solution to the previous solution, and if the new solution is close enough to the previous solution, we will say that the solution is reached. So from this point onwards, I am just going to talk about the first criteria, is whether the new solution is close enough to the old solution, and this epsilon value we need to take, that is something that we need to predetermine, is how exact we need our solution to be. For example, one way to choose this particular epsilon is this epsilon should be equal to, let us say, 10 to the power minus 4. Okay. For example, in this particular case of 2 minus x plus ln of x, the solution that we get are around 0.1, and the second solution that we get is of the order of 3. So what this particular criteria for the solution equal to 3 means is that the solution needs to be accurate in essentially up to the 4th decimal place. Beyond that, we do not care about with respect to the solution that we are trying to get. So if the solution is reached, okay, our x2 is going to be the actual solution. If it is not reached, we will increment I and we will go back over here and repeat this particular situation. Now the question is, before going back over there, we now need to ensure that x2 and the other solution is going to still bracket the true solution. So in this particular example, now because x2 lies on the same side of x star as xl, our new xl we are going to be replace it with x2, okay, and now x2 and xr are going to bracket this particular solution, okay. So what before we go to the next step, what we need to do is verify bracketing, and what that essentially means is, if f of L multiplied by f of 2 is less than 0, if f of L multiplied by f of 2 is less than 0, then what that means is xl and x2 are lying on the either sides of the solution. So we replace xr with x2. Okay. However, if f of xl multiplied by f of x2 is greater than 0, then we will replace xl with x2. Okay. So let us again look back at this particular figure that we had. F of xl is positive, f of x2 is positive, the product of these two terms is going to be positive. Therefore we are going to replace essentially xl with x2 because f of xl is because xl then is on the same side of x2. So now what we end up doing is, this is no longer our xl, this becomes our new xl. Okay. So now we will go back and we will then solve this particular expression with x3 equal to xl plus xr divided by 2. So we will now have x3 equal to xl plus xr divided by 2. Whether or not the solution is reached, we will check that criterion by subtracting xl from x3 and taking that absolute value, verifying whether that is less than our predetermined value epsilon or not. If it is less than the predetermined value epsilon, our solution is reached. If not, we will multiply fl with f3, verify if it is less than 0. If it is less than 0, then xr will be replaced by x3. If it is not less than 0, then xl will be replaced by x3. Okay. So let us again go back to this particular figure and see what we get. So the midpoint for this particular chord is over here, and this is our x3. Okay. when we consider f of x3 and multiply it with f of xl, we get the product fl multiplied by f3 is less than 0. If fl multiplied by f3 is less than 0, then we retain xl, but we replace xr with x3, and that is what I'll do over here, is replace xr with x3. Okay. So this essentially becomes our new solution xr, and we repeat that over and over again until we get convergence. Okay. And in order to repeat that, in this particular algorithm, I will replace all the purple parts essentially with the term I plus 1, and we will keep repeating that until we basically get convergence. Okay. So okay, and I'll just erase this part and say and if yes, okay. So essentially this is going to be our algorithm for the bisection method. Start with initial guesses, figure out a way to get the new solution x I plus 1. In the bisection method, this particular guess is just going to be the midpoint of the line connecting xl and xr. Check whether the solution is reached. If the solution has not reached, go back to the step 2 and repeat it over and over again until the solution is reached to a particular pre-specified criterion. Okay. So this is going to be our algorithm. Now what we will do is just go back to Microsoft Excel and try to look at the example of 2 minus x plus ln x example. We'll take a look at. If you do not have an access to Microsoft Excel, the other alternative that you can use is Google Documents. You can basically, if you have a Gmail account, you can go to google.com and use the Google Documents spreadsheet and essentially solve the same problem that we are solving over here. Okay, so let's look at this now. We'll just make it zoom to a full screen if possible. Okay, there we go. Okay, so the problem that we are interested in solving is the equation 2 minus x plus ln x equal to 0, and we know one of the solution lies between 1 and 4. Essentially that solution ends up being something like 3.14 or something. Okay, so let's type bisection method over here. What we have is we will start with two initial guesses. One initial guess will be x equal to 1, the second initial guess is x equal to 4. We will just call it iteration number 1. So what we will now do is calculate f of xl and f of xr. So we will just write that down, fl, and we will write this as fr. Okay, so fl is nothing but fl is equal to 2 minus xl. Xl is in this particular column, so 2 minus xl plus log ln of xl. Okay, so what we have done is, what we have over here is 2 minus b4. B4 is this particular cell, the b4 is nothing but xl, plus log of b4, which means log again of xl. Okay, we press enter and this is the value of f of l that is being computed, and then we can just take our cursor to the bottom of this cell and drag this cell to the right, and we will be able to compute our f of r. And if we click on the function key f2, we will be able to see the equation for f of r. So, f of r now is equal to 2 minus C4. So, C4 is essentially x of r plus ln of x of r. So, the plus ln of x of r. So, that is essentially our f of r. So, f of r also has now been computed. Next what we need to do is to compute x of I plus 1, and the way we will compute x of I plus 1 is, let us first write the heading x of I plus 1, okay, and x of I plus 1 is nothing but x of L plus x of r divided by 2. So, x of I plus 1 is nothing but average of x of L and x of r. What we next are going to do is then to calculate f of I plus 1 also. So, we will calculate f of I plus 1, I will write that down over here, f of I plus 1, and again f of I plus 1 equals 2 minus x of I plus 1 plus logarithm of x of I plus 1, okay, and that is what we have computed. Okay. The final thing that we also need to compute is the product f of L multiplied by f of I plus 1. So, that is what we need to compute. So, we will just do this and let us write that down over here. It is f of L multiplied by f of I plus 1. Font I will use is Times New Roman, so that we are able to see this very well. Okay. So, the product f of L multiplied by f of I plus 1 is nothing but this multiplied by this. Okay. As we know that if the product of f of L multiplied by f of I plus 1 is a positive number, that means essentially x of I plus 1 lies on the same side of the solution as x of L. As a result, we are going to replace x of L with x of I plus 1. So, if, so what we will write over here is if f of L multiplied by f of I plus 1 is greater than 0, then x of L is going to be equal to x of I plus 1, else x of L is going to be equal to the previous x of L. Okay, that is what we have written over there. And the same way, if this particular term, so if f of L multiplied by f of I plus 1 is greater than 0, okay, that means that x of r is going to be retained essentially the same value, else x of r will be replaced by x of I plus 1. Okay. So, this is what we have. So, this is our second iteration result, and then we compute f of L as before. So, we just go over here and drag it downwards. So, now instead of computing f of L, we have ended f of XL at this point, we have now ended up computing f of x of L at the new XL value. Likewise, we will just be able to drag this and this should work, and then we will drag x of I plus 1, and that is our new guess x for x of I plus 1, and then both of these guys we will just be able to drag. Okay. So, now what happens is that the f of I plus 1 at x I plus 1 equal to 3.25 is a negative value. If it is a negative value, now that means f of L is positive value, f of r is negative value, because f of I plus 1 is negative value, it is going to be xr that is going to be replaced now by x of I plus 1. So, what we will do now is just take this entire row and just drag it downwards, and that should be enough. So, what is going to happen is the procedure is going to be repeated at each and every row, and the stopping criterion is the error. Error is, as we had discussed earlier, error is nothing but absolute value of the difference between x of I plus 1 minus x of L. So, that is our error, and we just take this and drag it downwards. Okay, so this is how our error changes with each iteration. For the first iteration the error is 1.5, the second iteration error is 0.75, the third iteration error is 0.375, so on and so forth. Some of you might actually notice that every time we increase one iteration of the bisection method, we essentially are reducing the error by half. So in the first iteration error is reduced to 1.5, from 1.5 error reduces to 0.75, from 0.75 error reduces to 0.375, and so on and so forth. The stopping criteria, if you recall, that we had decided was that the error, the absolute value of the error should be less than 10 to the power minus 4. This is 1.8 10 to the power minus 4, which is greater than 10 to the power minus 4, whereas this particular value is less than 10 to the power minus 4. So this is going to be essentially our approximate solution, okay. And so what we will do is we will just color this yellow. So our approximate solution essentially is going to be, essentially approximate solution is going to be 3.1463. That's the solution that we have gotten through this procedure, okay. So to recap, what we did was we started off with a guess value of XL, a guess value of XR. The first thing that we did is computed f of XL, next we computed f of XR, next we computed x of I plus 1. The x of I plus 1 was quite simple, it is nothing but an average of the value XL and XR. What we did next was computed f of x of I plus 1. F of x of I plus 1 is nothing but 2 minus x of I plus 1 plus log ln of x of I plus 1, okay. That is what we did over there. Next what we had to decide was whether x of I plus 1 replaces XL or whether it replaces XR. In order to do that, we had to compute the product f of XL multiplied by f of x of I plus 1. So the product f of XL and f of x of I plus 1 in this particular case is positive. Now if this product is positive, that means XL and XI plus 1 lie on the same side of the solution. Because XL and XI plus 1 lie on the same side of the solution, it is XL that is replaced by x of I plus 1. So XL, the original XL was 1, we replaced it by 2.5, XR remained the same as before. FL is what we have computed using the new value of x of L. FR is essentially remains the same as we had in the previous iteration. Again we repeat the same procedure, we get x of I plus 1, which is nothing but an average of these two numbers. Remember this x of I plus 1 was an average of these two numbers, this x of I plus 1 was average of these two numbers, this x of I plus 1 is going to be average of these two numbers, so on and so forth. Again we computed f of I plus 1. Now when we compute f of I plus 1, what we see is that the f of I plus 1 is essentially negative. Because f of I plus 1 is negative, the x of I plus 1 lies on the opposite side of XL. So XL remains the same, but it is XR that we change and we update it to the newest value x of I plus 1, okay. So we keep repeating that procedure until the error that we get is reduced to below the threshold value of error that we had decided. So that is essentially how our bisection method is going to work, okay. So I will just write this as bisection, okay. So this is essentially our bisection method. What happens is that we started off with XL and XR at 1 and 4, reduced the value from 1 and 4 to its midpoint, which is 2.5. From the midpoint it went to the other midpoint between 2.5 and 4, which is at 3.25. Then we found a midpoint between these 2 points, which is 2.875, so on and so forth, each time replacing the particular solution XL or XR which is on the same side of the X star, that is the true solution. We keep replacing that and keep repeating this over and over again, and that is essentially our bisection method and the solution of the bisection method in Excel. The next method that we talked about was the reguli falsi method. The reguli falsi method is also a bracketing method. That means in reguli falsi, again we are going to start with two solutions. The two solutions are going to bracket the two guesses, I am sorry, are going to bracket the true solution as before. So again, going back to the overall algorithm that we had written for the bisection method, where we again start with the two initial guesses. Again we compare, we verify that the two initial guesses lie on either side of the true solution. We verify that by taking the product f of xl multiplied by f of xr, where if that is less than 0, this xl and xr are indeed admissible points for bisection or admissible points for our reguli falsi method. But in reguli falsi method, this particular method changes, okay, and how that changes we will look at the graphical representation of the reguli falsi, and then we will go on. The third part, the next part remains the same. If the solution is reached, we stop, we will take xi plus 1 as the solution. If the solution is not reached, okay, then we will either replace xl with xi plus 1 or we will replace xr with xi plus 1, and we will continue further. Okay. So this part, again all these part remains the same, okay, it is only this part where we are going to change. Okay. So let us go back to the figure that we had previously drawn. We will again start with the same xl and same xr. And I will erase the points that we had generated using our bisection method. Okay. So in bisection method, what we did was we looked at this particular segment and reduced it by half, and we proceeded. The other alternative to do this is essentially to draw a straight line connecting these points. Okay. Draw a straight line connecting these points and find out the point at which that particular straight line intersects the x axis. So we will take this and we will draw a straight line. Perhaps that straight line will go So this is a straight line that we are going to connect between these 2 points, and the point where the straight line intersects the x axis, we are going to call that as our x3, okay, sorry, our x2, okay, and then we will keep repeating this procedure again and again till we reach our desired solution. So now the question is, what is really this particular point? The point over here is the x coordinate of that point is xl and the y coordinate is fl, okay. And since we are no longer using the bisection method, but we are using the reguli falsi method, I will just write that down over here. Okay. So this particular point is xl fl, this particular point is xr fr, okay. So the line connecting xl fl with xr fr we can write is y minus fl divided by x minus xl is going to be equal to xr, sorry, is going to be equal to fr minus fl divided by xr minus xl, okay. This is the it's straightforward to get this particular expression. This is just a straight line joining the 2 points XLFL, XRFR. Okay. Now the point of intersection of this particular straight line with the x axis is obtained by putting y equal to 0 over here. Okay. So the point of intersection of this this particular curve with this particular line with the x axis is going to give us our new initial guess. So this particular point that I have shown over here is nothing but the point x I plus 1 comma 0. Okay. This particular point lies on this curve, so it satisfies this particular equation. So when we substitute these values over here, what we are going to get is essentially 0 minus FL is going to be divided by xi plus 1 minus xl is going to be equal to the right hand side. So I'll just modify that over here. So what we'll get is 0 minus FL divided by xi plus 1 minus xl is going to be equal to the right hand side. Okay. And we can just rearrange this equation in order to get the particular the solution for xi plus 1, and that solution is essentially going to be xi plus 1 is going to be so we will just invert that and take f of xl on to the other side. So we will have xi plus 1 minus xl is going to be equal to xr minus xl divided by fr minus fl multiplied by minus f of l. Okay. Or we can also write this as xi plus 1 equal to x of l minus f of l multiplied by xr minus xl divided by fr minus fl. Okay. So instead of generating xi plus 1 equal to xl plus xu divided by 2, xl plus xr divided by 2, we have just generated it using this particular method. Okay. So we will just replace the step number 2 in our bracketing method over here with the result generated just now. So we will say xi plus 1 is going to be equal to xl minus f of x of l multiplied by x r minus xl divided by fr minus f of l. Okay. So this is the only thing that has changed when we go from a bisection method to a regular falsi method. Okay, keep in mind f of l is nothing but f of x of l, f of r is nothing but f of x of r. Okay, and this is what will get as the overall algorithm. So we will choose fl, we will choose fr, we will then use this particular expression in order to get the new value of xi plus 1, compare xi plus 1 with xl. If it is less than epsilon, the solution is reached. If it is not less than epsilon, figure out whether xi plus 1 lies on the same side as xl or whether it lies on the opposite side of xl. If it lies on the opposite side of xl, our xl will be replaced by xi plus 1. If it lies on the same side of xl, or if it lies on the opposite side of xl, xr will be replaced by xi plus 1. If else, it is xl that will be replaced by xi plus 1, so that we ensure at each point that the two solutions are definitely, the two guesses are definitely going to bracket our true solution f x star. Okay, so now let us go back to Microsoft Excel and try to see how we can solve the same problem 2 minus x plus ln x equal to 0, this time using essentially not the bisection method but the reguli falsi method. As we had seen a few moments back, the difference between bisection method and reguli falsi method is only in the way x of I plus 1 is computed, remaining everything remains the same. So because of that, for just to save some time, what I will do is I will just copy this particular worksheet by clicking on move and copy. I will just create a copy of this worksheet before sheet 2. Okay. So now what we have is a copy of the worksheet in which we use the bisection method. I will call this regula falsi. Okay. And in regula falsi, again we are interested in solving the problem 2 minus x plus ln of x equal to 0, this time using regula falsi method. Okay. So what I will do is really all these values I will just delete them. Okay. And then okay. So now we have our original worksheet, the first row of the worksheet that we had used for the bisection method, and that is what we will use essentially for our regula falsi method. So our XL, again the same way as before, we start with XL equal to 1, XR equal to 4, we compute our f of x of L in the same manner as before, we compute our f of x of R in the same manner as before. Now what changes is how xi plus 1 is computed, and the way, so what I have done is just deleted this x of I plus 1, and because this x of I plus 1 does not have any value in it over here, that is why we are getting an error when Excel computes its solutions. Okay. So x of I plus 1, if you recall, was equal to x of L minus, okay, we had x of L minus f of L multiplied by XL minus XR multiplied by XL minus XR divided by FL minus FR. Okay, this is our x of I plus 1. Okay. So again what we have done is I will just write down the equation for x of I plus 1. X of I plus 1 is nothing but XL minus f of L multiplied by x of L minus x of R divided by, in brackets, f of L minus f of R. Okay, this is what our and just to make it easy to read, I will just make it into Times New Roman. Okay. So in now let us look at the function that we get over here, f x of I plus 1. So what we need, x of I plus 1 is nothing but XL, which is the column B row 4, that is B4. So XL is B4 minus f of L, which is D4, multiplied by B4 minus C4, right, B4 minus C4, which is x of L minus x of R, divided by f of L minus f of R. F of L is in basically D4 and f of R is in E4. So what we have is B4 representing x of L minus D4 representing f of L multiplied by B4 minus C4, which represents the difference x of L minus x of R, divided by D4 minus E4, which represents the difference f of L minus f of R. Okay, this is what we have over here. Once we get x of I plus 1, we will compute f of x of I plus 1 in the same manner. Again, we have not changed it from what we had done in the bisection method. Remember, when I was showing it on the board, all we did was we replaced the way in the second part, the second step, in that is the way we compute x of I plus 1 given given xl and xr. That is the only thing that changes. So f of I plus 1 is nothing but 2 minus x of I plus 1 plus ln of x of I plus 1. Okay, we get the product f of l multiplied by f of I plus 1. Because this particular product is positive, that means essentially x of I plus 1 lies on the same side of as x of l, and we replace x of l with x of I plus 1. Okay, so what we are now going to do essentially is really just take these guys and just drag them below, and this is going to be our new x of I plus 1. Okay, and likewise we will have a new value for error as well. Okay, so this is the result at iteration 2, and if we want to get the results at iteration 3, 4, 5, 6, 7, 8, so on and so forth, we just highlight the entire row, go to the right bottom edge of that row and just drag it downwards, and let us drag it until say 10 iterations. Okay. So this is what happens in 10 iterations using the regular falsi method. We started with 1 4, the next value of x of I plus 1 is 2.8859 and so on and so forth, and as you can see our stopping criterion was that the error should fall below 10 to the power minus 4. So this is the point where the error has fallen below 10 to the power minus 4, and this is going to be the solution that we get. And again we will highlight this solution, and we really do not need any of this data, that is redundant data. So when we are using the regular falsi method, now what we actually have is basically in about 5 iterations we have gone from the initial solution of 1, 4 and we have finally reached the actual solution 3.14615. Okay, that particular solution is accurate within the desired accuracy that we had selected, that is 10 to the power minus 4. Okay, so now what we will do is just take a few minutes before finishing off this lecture, take a few minutes to just recap what we have done in this particular lecture. So what we have done in this lecture is, initially we gave an overview of what we mean by nonlinear equation solving. Nonlinear equation solving is nothing but finding out the points at which any curve f of x intersects the x axis. That is the interpretation, the geometric interpretation when we look at this problem in a one dimensional sense. So that is the geometric interpretation of solving the nonlinear equations. We then talked about the various methods of solving the nonlinear equations. The methods came in two categories. The first category was bracketing method, in which we start with two solutions, and the two solutions are going to bracket our actual solution x star. At each point of time we will ensure that the two guesses are going to lie on either side of our true solution x star. That is what we did in both the regular falsi method as well as the bisection method. The way bisection method worked is, we take an initial segment, for example in the example that we took, we took the segment between x of l equal to 1 and x of r equal to 4, and at each iteration we half the overall length of segment. So the length of segment from 3 it went to 1.5, from 1.5 it went to 0.75, 1.75 it went to 0.375 and so on and so forth, and we slowly converge on to the true solution x star. That is what we did in the bisection method. Then we covered the regular falsi method. In the regular falsi method, the overall procedure was the same, except the way we found the solution x of I plus 1, the next guess of the solution x of I plus 1, and the way we did that is, we joined the point xl fl and the point xr fr, we joined it with a straight line and found the point where that straight line intersects the x axis. That became our new guess. So that is how we covered the two bracketing methods, bisection method and the regular falsi method. In the next lecture we are going to cover the open methods, specifically the fixed point iteration, the Newton-Raphson's method and the secant method. Okay. Thank you and see you in the next lecture.